around a circuit loop, in case you've got more than one cell, the sum of the EMFs equals the sum of the potential differences around the loop. And when we use EMF and potential difference in this definition, we're using EMF to apply to sources of electrical energy, and potential differences apply to the things in the circuit that use electrical energy. And you may want to watch the lesson on voltage and EMF if you're not clear about that. Here's a circuit. There are two unknown voltages. How can we work them out? You can pause the video and think about it for a moment. Well, let me tell you, there isn't a single circuit loop to help us do this. We've got to identify some specific loops. That means where we start at one point and go round the circuit and come back to the same point. So let's take the loop shown in yellow. We're starting at the positive terminal, going round through the two resistors and back to the negative terminal, then back to the starting point. So that's one complete loop. That loop isn't affected by the other things in the circuit. There's a cell and two resistors in this yellow loop, and we can apply Kirchhoff's law to the yellow loop and forget about the rest of the circuit. We could also say there's a green loop, this outer loop, going from the positive around the top, around the single resistor on the right hand and back again. That's another loop, and we can apply Kirchhoff's law to this loop. There is a third loop shown in red. This is a bit awkward. First of all, in this loop there's no cell or battery, and the direction of the loop conflicts with the direction that the current is passing. If we take the conventional current as going positive to negative, the direction of the loop is conflicting with that. The current in the left side and the current in the right side are both going down. So the direction of the current doesn't match the direction we want to go around the loop. And this would make our life quite tricky. And I'm not going to discuss this beyond saying that we'd have to make the voltages across a resistor negative to allow for the fact that we're going in an opposite sense to the direction of the current. Let's use the yellow loop and the green loop to work out the problem. So, if you pause the video, have a go. Can you work out the missing voltages? Here's the answer. Let's go around the yellow loop, the first loop. The voltage from the cell, from the power supply, the single cell, is 2 volts. And that must add up to the other voltages in the loop. So that's 0.3. The voltage across the lower resistor must be 1.7, because 0.3 and 1.7 add up to 2, the same as the battery's voltage. Go around the outer loop. Well, there's only one component. There's a resistor. So the voltage across the cell of 2 volts will be equal to the voltage across a resistor. So that right-hand resistor has 2 volts across it, the same as the cell. One useful thing we can note is that if we've got a part of a circuit, for example 3 resistors in series, the full circuit isn't shown, there may be current going through the 3 resistors, and suppose we have 3, 5 and 2 volts across each of them. What would be the voltage between the left hand side and the right hand side? If we could connect a voltmeter between the left and the right, what voltage do you think we'd get on the voltmeter? The answer is 10 volts. And if you think in terms of energy, it's easy to see why you can just add up these voltages. The 3, 5 and 2 represent 3 joules, 5 joules and 2 joules per coulomb. So in total, between the left and right sides, you'd have 10 joules per coulomb being turned to heat. So the total voltage between the two ends we can find by adding the individual voltages across that part of the circuit. When we look at voltages for objects which are in parallel, we can see that voltages for things in parallel are equal, here's 3 resistors connected in parallel to a cell. If we go around the first loop, I hope you can see that the voltage across a resistor will equal the cell's voltage. But we could go around the second loop through the middle resistor, and there's only one resistor in that circuit. So for the second loop, the voltage across the middle resistor is also just equal to the battery's voltage. I should say the cell's voltage. And for the outer part of the circuit, the right hand resistor, again there's only one resistor in that loop. So the voltage across the resistor will equal the voltage across the cell. So all 3 resistors have the same voltage, and this is true of any components in parallel. They always have the same voltage across them. Okay, and that just about covers what we need to say. In some textbooks you'll find a more advanced definition of Kirchhoff's second law. I just briefly want to comment on it. A more advanced definition is this: the algebraic sum of the potential differences around a circuit loop equals 0. Now in this definition we don't use EMFs anymore. We simply say that everything in a circuit loop has a potential difference across it. Some things have a positive and some things have a negative potential difference. And we have a sign convention which will depend on the direction of the current and the polarity of batteries, for example. We'll have a sign convention which means we can give each voltage, each potential difference a positive or negative value. And if we follow the sign convention, we'll find that the sum of the potential differences around a loop always add up to 0. I hope that's useful. The basic thing to remember is simply that